I have my ray box back, and today we are going to talk about refraction. And refraction is the bending of a wave as it transfers from one substance to another. For light, it means to be going into different substances. So I'm going to take this piece of plastic that I have, and instead of changing the ray box, I'm just going to change it and move it. And you should be able to see that ray that's on the inside, right there, is definitely bending from one to the other. Okay, if I were to trace these two rays, it's not exactly straight, you would see they run parallel. So in the air, they travel the same. It's just that when I had this in the way, depending on how much I bend it. So here's what's happening. Light is traveling, the wave is traveling through air, which means it's pretty fast. It's hitting this substance, which is transparent, so it can go through it, causing it to slow down, and that makes it bend. And when it comes back out here, it speeds up. And we can get all sorts of kinds of bends. So I have some different kinds of shapes here where you can see some of the bending as it goes through. We'll talk more about what happens. There's a little reflection off this surface as well. If I have all of the light, you can see it bending. Again, we have some internal reflection here. Let's go back to just a skinny, let's go to a little bit skinnier beam of light. You can see it a little bit better this way. So this is like an isosceles, no, this is an equilateral triangle. No, it's not, it's an isosceles. Here's another example where it bends, and you'll start to see, oh, got a rainbow. Then we have something that happens called internal reflection. We'll get to that more. And here's just an isosceles triangle. Or sorry, this one's the equilateral. And you can see that as the light travels, it's going to hit and it's going to bend. We're going to mostly deal with flat surfaces. And when the rays of light come in at different angles, the more angle there is, the more bending. Oh, there goes a motorcycle. All right, so you don't really need a ruler, but it could help. We're going to do some drawings and some notes, so let's get to it. Turn that one off. All right, so there's a little video, and I'll probably just have you show this in class to show how this works for water waves. And the link is here. So again, refraction is the bending of a wave as it passes from one medium to the next. In water, it's shallow and deep. And you can see here, I have some shallow water and some deep water. And here's the wave. And as it changes and goes through these different depths, there's a bending. That's what it looks like for water waves. So there's some rules and things that happen when light waves travel. When the light travels in less dense, meaning like air, for example, a lower index, as there's numbers assigned to different transparent substances that give it this, how much bending will occur. The wavelength will get shorter, which is not something you can see for light, but you can definitely see here the difference in these wavelengths. It will slow down. You can see a difference in where these are, showing it slows. One thing that doesn't change for any wave is the frequency and the period. The amount of waves, again, this is shown in the water. These are still the same number of waves, even though they're bent. The wave numbers don't change. And waves bend away from the normal, which I'll show when we do our pictures. And then everything reverses when we are in a higher dense, when we go into a, like, diamond or glass or lucite. So let me move this paper here, it's gonna bother me a little bit. Okay, so indices of refraction. First of all, we use the letter N, and there's a number of them that you need to know. Water, 1.33. Diamond, 2.42. Air, which is technically a vacuum, 1. Flint glass, 1.61. And these can all, you can look them up. These are just some of the more common ones we're going to use. Quartz, benzene, 1.5. Glycerol, same as quartz. Notice there's no unit on these. Lucite, yes, you have to add these in. And crown glass, 1.52. So, all right, so the relationship is very much a geometry type relationship, so make sure you're adding those in. So in general, the index of the first substance times the sine of its angle will be equal to the index of the second substance times the sine of the next angle. It's called Snell's law. Sometimes, instead of calling it substance 1 and 2, like if it's water, we might say the index of water times the sine of water. Might be the index of glass times the sine of glass. So sometimes instead of using 1s and 2s, we just use the variables. All right, so this is going to require your calculator to be in degrees, not in radians. So there's the first thing. So as we do these practice problems, you need to make sure you are in degrees. And you will definitely need your calculator. All right, so first we're going to ask you to draw a picture. When you do practice problems, I'm going to make you do this. So I draw a line. That's the in between the two substances. So a ray of light is going to pass from carbon tetrachloride to air. So there's my two substances, top and bottom. Carbon tetrachloride is 1.46, air is 1. Then you need to draw a normal. And again, you don't need a ruler necessarily, but do as straight as you can. The normal should be dotted. So a ray of light passes from carbon tetrachloride. So, and again, these are not going to be to scale. So I'm going to have a ray of light coming into this interface at 30 degrees. Okay, the angles are always from the normal to the ray, always, just like in reflection. Now, let's find the refracted angle and talk about it. So I'm going to say the index of carbon tetrachloride times the sine of the angle in carbon tetrachloride is going to equal the index in air times the sine of theta air. Again, I'm not using 1 and 2, I'm just using letters. Okay, so 1.46 times sine of 30 equals 1 times sine of angle air. Again, make sure you're in degrees. All right, 1.46 times sine of 30 is 0.73, and then I divide by 1. So I'm at 0.73 equals sine theta A. Now, we haven't done this in a while, but how do I find the angle? So second sine 0.73. So the angle in air is 46.89 degrees. If this is the normal, 30 would be straight, so it's going to bend away from the normal. Okay, so this is 46.89. By being bigger, we call this bend away from the normal. The other thing that happens is when you have a larger angle and you bend away from the normal, okay, the velocity of the wave is faster. So by pictures, if I have a bigger angle here, I'm always going to know it's faster. I'm also going to always know it's a lower index of refraction. And then reverse it. This means over here, it's a higher index of refraction, which means it's more towards the normal. The velocity will be slower. All right, so this is a picture you're going to see, this next one, on quizzes and on tests. So pay attention. Multi-layers. So angles in the same substance will be the same. Given a ray of light traveling from 60 degrees from air. So I'm going to kind of draw this. It's not perfect. This is the first ear. 60 degrees. There's my normal. And it's going to go to water, to flint, to air. So as far as velocities, I can already tell. So from air, it's going to be fast. It's going to get slower. Now it's going to get slower. Sorry. And then it's going to go back to fast. The higher the index, the slower. And then the angles, we know that the angles, if I go higher, the angle's going to get towards the normal. If I get even higher, it's going to go more towards the normal. And we're going to make our picture kind of match it. All right, so let's do Snell's law for each system. Okay, so from here to here. So 1 times the sine of 60 degrees is going to equal to water, 1.33 sine theta W. And this is again why instead of using 1 and 2, it's easier to remember. All right, so 1, well, I don't really need to do that, times sine of 60, right, equals that, divided by 1.33, and then second sine, I'll just do second answer, 40.63 degrees. Okay, so 40.63, which is smaller than 60. 40.63. And when it strikes here, give it a normal. Geometry theorem, two parallel lines cut by a transversal. Guess what? This is also 40.63 degrees. All right, let's do the next layer. So now it's water, 1.33 times sine of 40.63 equals the next layer, 1.61 times the sine of theta. I'll just use F for Flint. Clear. Okay, 1.33 sine of 40.63, enter. And then we're going to divide by 1.61. And then second sine, second answer, 32.54. It is getting closer, so 32.54 degrees. So I'm going to make that even smaller. I'm going to label it like this, 32.54 degrees, make a normal. That means, oh, that's not very straight, is it? So that one's also 32.54 degrees. Now, technically, as this thing is going this way, I can put arrows showing it going through. It's going to bend, and it's going to bend, and then it's going to bend one more time. This is incident, this is refracted. This is incident, this is refracted. This is incident, this will be refracted. It's not a huge issue, but all right, so let's do the last one. So I'll just do it over here. So we're going to have 1.61 sine 32.54 equals 1 times sine of theta A. Well, let's do it. Okay, 1.61 times sine of 32.54. Obviously, we're dividing by 1, so I don't really need to do that. So second sine, second answer. And look at that. 60 degrees. So that's going to bend away. I'm exaggerating it, but I want to make it show the bend. And there's my arrow. Didn't need to actually do that one because in the same substance, the angles will be the same. So if I knew this was 60, this would be 60. I don't even have to do the math, but this just helps show you. All right, so when you go from low to high, you get slower and then you get faster. All right, when you go from low to high, you bend toward the normal. You go to low to high, you go toward the normal, but then when you go from a high to low, you go away from the normal. So that's what it means. And when we draw the pictures, we try to show the bends a little bit. I know this one looks kind of straight. I guess could have gone a little bit better. All right, we're going to do some practice.